Hi and welcome to the video lecture series on thin film flow modeling and simulations in the course M7033T Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work in the Division of Machine Elements here at Luleå University of Technology. Now, this is the fourth part of the second video lecture on the introduction and underlying theory, and here we'll learn about different constituents of the Reynolds equations, such as the film thickness equation, compressibility, pressure viscosity relationship, and a little bit about lubricant rheology. Hi and welcome to the video lecture series on thin film flow modeling and simulations in the course M7033T Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work in the Division of Machine Elements here at Luleå University of Technology. Now, this is the fourth part of the second video lecture on the introduction and underlying theory, and here we'll learn about different constituents of the Reynolds equations, such as the film thickness equation, compressibility, pressure viscosity relationship, and a little bit about lubricant rheology. As you know by now, the Reynolds equation is a lower dimensional model, so that for 2D flow it is 2D, and in coefficient form it reads like this, and here we have the time-dependent variant for incompressible isoviscous flow in Cartesian coordinates. But it may also be formulated in conservation form, looking like this, and here the first term then is the accumulation or loss of volume in the system, and the second term, the divergence term, represents, as you know by now, the Reynolds equation is a lower dimensional model, so that for 2D flow it is 2D, and in coefficient form it reads like this, and here we have the time-dependent variant for incompressible isoviscous flow in Cartesian coordinates. But it may also be formulated in conservation form, looking like this. And here the first term then is the accumulation or loss of volume in the system, and the second term, the divergence term, represents the difference between the flow that comes in and the flow that goes out, and the flow itself here is a vector valued function for the volume and represents the volume flow, now given by the expression below. And of course, if you insert that into the divergence operator, you will end up with the coefficient form as of above. We have talked about the components of the Reynolds equation before, but here in the following we will look a little bit more deeply into the film thickness, here denoted h. So h is a function that represents the clearance, the separation, or film thickness, dependent on how you would like to express it, and it may be dependent on various things really. And for rigid surfaces, so if both the upper and lower surfaces that hopefully will be separated by this lubricant film are rigid, then the film thickness is known at least up to some constant that quantifies the actual clearance. So this constant may depend on the applied load, it may depend on speed, and may depend on viscosity, as you will find out later in the course. If the surfaces may deform, if they are deformable, then the film thickness or clearance will be dependent of the pressure via the deformation. And we can include that into the film thickness equation by adding the deformation as a part of the film thickness description. So we have the first part here would be the constant that we can determine by means of force balance or load balance. The second one describes the initial undeformed geometry of the both surfaces, and it's a combination of both, so it's similar as what we learned in the contact mechanics part of the course. It's the gap between the surfaces. And then the last bit is deformation due to pressure, which we may for some particular problems approximate with the Boussinesq type of deformation pressure relationship that we have been exploring quite a lot before. Another constituent in the Reynolds equation is the pressure-density relationship, which models the compressibility of the lubricant. And obviously gases are compressible even at very low pressures, but at higher pressure even liquids become compressible. Two examples of constitutive relations between density and pressure will be given here. And the first one is the Dawson and Higginson semi-empirical model. So they had some oil data and they fitted an expression, exactly this expression as we see here, to that data, and they had three parameters in their original model, and they are the rho A and D1 and D2 parameters, or at least parameters related to those. PC here is cavitation pressure, which is added to the model at a later stage. And the figure, it is not coming from Dawson and Higginson's work, it's from a work by Saline et al., where they explored different compressibility relationships for cavitation models. So just to better explain what a semi-empirical model is, I was myself browsing and I found this definition of Merriam-Webster very practical, and it aligns at least with my own intuition about it. So it tells you that a semi-empirical model could be a mathematical model that describes results obtained by experiments. Okay, exactly not that wording, but that's my interpretation of it. The second constitutive relation is the constant bulk modulus one. So beta is typically used to represent this constant bulk modulus, which is defined as the density times the derivative of pressure with respect to density. If beta is constant, then we can integrate this expression and we obtain this explicit exponential relationship between pressure and density, as you can see here. So it's a two-parameter model if you do not regard cavitation pressure as a parameter, but it has the ambient density rho A and it has the bulk modulus coefficient beta. And if the constant bulk modulus is considered as constant, this relationship can be integrated to yield exactly this explicit relationship, an exponential relationship between pressure and density. And if we do not regard the cavitation pressure as a parameter, this is only a two-parameter model, the ambient density rho A and the constant bulk modulus beta. And in the figure you can see that we have plotted four different curves. Okay, the X marks the measured mineral oil data, and then we have a continuous black line which is actually following this data more or less exactly, and it's when we have fitted the D1 and D2 parameter to that data, in the Dawson and Higginson semi-empirical model. So you can see that it's very well suited to represent the pressure density relationship for this mineral lubricant in a whole range between 0 and 1 gigapascal pressure actually. But if you take the original curve, which was for another lubricant, you can see that that lubricant must have behaved quite differently, because with the dashed dot line you have the Dawson-Higginson original semi-empirical relationship, which has other coefficients, or not coefficients, parameters D1 and D2 than the one that we fitted here. And moreover, in this curve you see the double dash line for the constant bulk modulus representation, and it is good up to, let's say, 100 megapascals or so, but then discrepancy starts to evolve, of course, since this is an exponential relationship, and it does not at all behave like that, this mineral oil, when it's subjected to high pressures, as we can see. One note here is that on the y-axis of the figure we have a variable called theta, and theta is just rho divided by rho A, so it's a dimensionless density, one can say, and therefore all curves starts at 1 instead of rho A. Another constitutive relationship included in the Reynolds equation is the pressure-viscosity relation, and Barre's law is a semi-empirical first approximation for small or up to moderate high pressures like 0.5 gigapascals. And this one, the Barre's law, has been obtained by fitting a straight line to the logarithm of the viscosity with respect to pressure, and that means that we can compute the pressure viscosity coefficient alpha in this way. And that also means, and if we look at the diagram, a semi-log y diagram, where we have on the x-axis a linear scale for pressure from 0 to 1 gigapascal here, but if we then restrict now this model to be valid in region up to 0.5 gigapascal, we can draw linear lines here, linear relationships between the pressure and the logarithm of the viscosity, the dynamic viscosity in Pascal seconds here plotted on the y-axis. And for two different alphas, of course, these will be just different slopes, will just reflect different slopes of this relation. Hi and welcome to the video lecture series on thin film flow modeling and simulations in the course M7033T, Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work at the Division of Machine Elements here at Luleå University of Technology. Now, this is the fourth part of the second video lecture on the introduction and underlying theory, and here you will learn about different constituents of the Reynolds equations, such as the film thickness equation, compressibility, pressure viscosity relationship, and a little bit about lubricant rheology. As you know by now, the Reynolds equation is a lower dimensional model. Higher pressures, they will require more complex models. For example, the free volume model. And it's given here, where the ratio between the volume and the V0 volume is given by yet another expression. And here you can see it's no longer a two-parameter expression. There are many more parameters than that involved to express the viscosity, in this case the viscosity pressure relationship. And if we plot this, it will typically look something like that, the green and the yellow curve in the diagram. So it will not follow this straight line for that long. it will deviate, and we'll have some bends on that curve too. The lubricant rheology is not a constitutive relationship directly in the Reynolds equation, but it's really important, and it governs the way the fluid builds up the shear stress depending on the shear rate. And the shear rate is nothing but du dz. It's often denoted gamma dot, like you see here in the diagram. And when we have a Newtonian fluid, the shear stress is directly proportional to the shear rate. And here on the right hand side, you see a figure where we have the velocity field in this color height map. And at x1, the position x1, you can actually see the x component of the velocity plotted as a function of z from the lower surface and up to the upper surface. And since the lower surface is moving with u1, that's a boundary condition, you know, when we solved the reduced set of Navier-Stokes equations and obtained an explicit expression for u. So that's boundary condition, it's u's boundary condition on that side, and the stator surface, the upper wedge geometry part is stationary, so it has velocity equal to 0, of course, and we can see that clearly reflected by the white curve of the x component velocity. Now, as you understand, of course, the u dz is a varying function, and it actually has a 0. It has a maximum value. This constant of proportionality in the relationship between the shear stress and the shear rate, it is defined to be the dynamic viscosity mu. Note now that this is not reflecting cause and effect. It's not the shear rate that generates the shear stress, is it? It's the shear stress that generates the shear rate. So we should turn this in the manner described there. And then we get a better picture of the cause and effect. For a non-Newtonian fluid, the shear stress is not proportional to the shear rate. So the dynamic viscosity is not constant. And one example of a non-Newtonian fluid is the double Newtonian fluid Corot model, according to the Corot model, which we see here. So here we have a viscosity mu, which changes from mu1 to u2 dependent on the shear rate gamma dot. Another non-Newtonian model, another model for a non-Newtonian fluid, I should say, is the limiting shear stress model by Gissim and Weiner. And you can see it here, and it includes the limiting shear stress tau L, which actually limits the build-up of shear stress with shear rate. So for higher shear rates, it will remain constant at the limiting shear stress level. Hi and welcome to the video lecture series on thin film flow modeling and simulations in the course M7033T, Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work in the Division of Machine Elements here at Luleå University of Technology. Now, this is the fourth part of the second video lecture on the introduction and underlying theory, and here you will learn about different constituents of the Reynolds equations, such as the film thickness equation, compressibility, pressure viscosity relationship, and a little bit about lubricant rheology. As you know by now, the Reynolds equation is a lower dimensional model, so that for 2D flow it is 2D. and in coefficient form it reads like this. And here we have the time-dependent variant for incompressible isoviscous flow in Cartesian coordinates. But it may also be formulated in conservation form, looking like this. And here...
Okej, let's go! Ser ni? Luftsmörjning är möjligt. Hur fort går det då? Fascinerande. Fascinerande. Nu börjar det... Jag tyckte jag hörde något. Nej, i helvete. Jag hör ingen kontakt ännu.
Det är lite obalans, man ser axeln rör sig lite, det är lite jämvikten är inte 100.
Ja, men den kan ju också komma sig av att den är ju faktiskt inte plan, va? Och då får du nu har vi den. Ha! Häftigt! Oj, vad vackert!